The content today is that we first dive a little bit into some basic usage of the sequencer, and then in the second half of the meeting, we will go into different scenarios, how to solve different tasks and various tasks with the sequencer, and give you some ideas how to use it. Okay, let me share my screen. So I hope you can see my screen. There should be SweepMe being open, what you can see now. And the first thing that we start with is to see how does the SweepMe sequencer actually look. Basically, you can use the SweepMe sequencer with just a single module. Every module itself works already in the sequencer. For example, I can add a delay, give it a value, let's say 1 second delay, and I can run this program. It does not have any big meaning or make sense, but it already runs. What SweepMe often does, or typically does, is when you have forgotten make file module, it adds a make file module so that your data is saved. If you don't want to save data, you can switch it off, and then you can still run the measurement and no data will be saved into a text file. Okay, the basic concept of SweepMe is to make loops and repetitions. This is often needed for parametric testing, especially, for example, in the semiconductor field. In parametric testing, you want to go through, for example, different temperatures, different voltages, different motor positions, and so on, and want to screen a parameter space and collect all the data from the instruments to save them and evaluate them later on. And SweepMe, and the name sweep comes from sweeping parameters, is exactly made for this purpose, to sweep parameters. To do this, let's take a simple loop module. The loop module can also do repetitions. It does not sweep a value like a voltage or temperature, but it can sweep an index. So it is also part of this concept of doing a sweep over index or indices. Here I will enter, for example, 10. Now we can run a measurement and we can plot this data, and let's plot the index over time. So what you can see is that the index 1, 2, 3, 4, 5 is growing over time, and we made some kind of a measurement without a big, it's not a real measurement in terms of that we get real physical data, but it is already a procedure that we're running through. And the concept of SweepMe or of the sequencer goes further, that every module has basically the chance to make a repetition or an iteration. So we can also add another loop module. And here I can actually, for example, add 5. So let me show you what this does. You can see now some staircases here, because we plot here the loop 1 index. This means this is the index at which loop module 1 is. The loop module 1 makes 10 iterations, so we get 10 steps. And at each step, we iterate 5 times loop 2 module. So we can see that loop 2 module is increasing its index, but because we don't plot loop 2 index, we just see loop 1 index here, and this stays at 1. Then it goes to 2, and so on. To slow down this a little bit, we can add a delay module. I can, for example, also add this just to the top and say 0.5 or 0.2 seconds, probably enough, and run it again. And you can see here also in the sequencer how the first module runs through its iterations, and for each value of the first module, of the first loop module, you can see how the second module makes iteration from 1 to 5, 1 to 5, and so on. I can also go to the plot and add the loop 2 index here. And then it looks like this. Because loop 2 is always going from 1 to 5, and when loop 1 is at 2, it goes again from 1 to 5, from 1 to 5, and from 1 to 5, and so on, right? So this basically shows you how you can easily nest modules, and for each higher iteration below, or these nested iterations create nested for loops, and you can go through a parameter room. For example, the loop 1 module could be a temperature controller that is going through temperatures, and loop 2 could be also a module that is applying a voltage. So you get automatically for each temperature a voltage sweep. This concept can now be extended by having also multiple branches. For example, we can add another loop module. I basically take here just loop modules to keep it really simple. at the end, you typically replace this with modules that make that interface with instruments and do some variations there. I can add another loop 3 module and open a new branch. This loop 3 could be maybe 3 iterations, and we can add a new plot. And also plot this loop 3 over time. So let's run this. It will first run through the 10 iterations of the first branch. And then it makes 3 measurements in the loop 3, in the second branch. Yeah, this basically shows that SweepMe is running through one branch and is fulfilling all the sweeps that are here in this sub-branch. And once this is finished, it goes to the next branch. And again, you can do some variations over some voltages, temperatures, and so on. It is also possible to put the loop 3 into the loop 1 module. Then you basically have 2 branches again. For the first iteration of loop 1, you do 5 iterations of loop 2, then 3 iterations of loop 3. Then again, loop 1 is measured. Let's run this. And what you can see here is that maybe I should switch off here this loop 1. You can see how this jumps between the 2 branches. And always loop 2 is measured 5 times. Then loop 3 is measured 3 times. And you can see it also here in the plot. We can basically also split the data for each iteration of loop 1. We want to have a new color. And we also want to have a new color for each iteration of loop 1 here in the second plot. And you can see how it always makes a new line for each thing. So this is also an important thing to do. For example, you have a wafer prober here at the top that goes through different positions. And this loop 2 or loop 3 could now present different measurements that you do at every wafer prober position. For example, a voltage sweep or a capacitance voltage sweep and so on. So you can nest different modules, not only that you create completely new branches, you can also have sub-branches that do their tasks for each higher variation. So this is essentially the basic concept of SweepMe to do these nested variations. For many tasks, this is fully okay. And once you get the system, you can create already a handful or a lot of measurements. Now, let's go through which module is active at which time. You can see that I put a delay module at the top, and it has an 0.2 hold value. And this delay module is basically in 2 branches at the same time, because it is in the branch delay make file loop 1 and loop 2. And it is in the branch delay make file loop 1 and loop 3. These are these 2 branches that SweepMe has. And this means when you have a module that should be active in all the branches that you have, then put it very high into the sequencer, right? Then it will be always active. And for example, here the delay is used to delay down the sweep time. And then, of course, you put it very high, and it will automatically be applied to this variation in loop 2 and in loop 3. This said, it also means that when the first branch is active, for example, loop 2 is doing something, also loop 1, make file and delay are active and always at each step doing their task. This can be saving a file, returning their current index value, or delaying a certain time. And the same thing holds true when you go to a second branch. Again, all the modules that are in the second branch, like delay, make file, loop 1, loop 3, are doing a certain task and are active. So the programming in the sequencer is fundamentally different from a typical programming in Python or MATLAB or any other programming language, where you have your programming with if-else, and you do a certain task, then you do the next task. In SweepMe, it is different because here you have always branches. Branches means you can do iterations in one branch, and basically these modules in one branch are active and can do certain jobs, like testing for a condition, applying values, reading back values. So in SweepMe programming, it is more about which modules are active at a time. Now, let's go. Let's see what is the meaning of the order of the modules. What's the difference when I change modules in the order? For Makefile, for example, the order is very important because for each higher variation, we write a new file. Let me show this in the folder structure. We write a new file. This means at the moment, Makefile is more or less at the top of the sequencer. Delay has here no meaning. It has no further variations. So we are writing one file to our temporary folder right now. This is this file. If I put the Makefile a bit one step lower, it is creating 10 files now because loop 1 is doing 10 variations. It is above Makefile and it creates 10 variations. And you can also see this here. So for Makefile, this has an important meaning where to place it. But does it have a meaning for the delay module where to place it? The delay module could also be put here. It will still be in the active branch. For each combination of iterations, it will be making its job. This is delaying the time. So basically, this has absolutely no difference. This does absolutely make no difference whether you put your delay here, because delay will anyway, for every repetition, delay 0.2, whether it is on the top or at the bottom. It is part of this active branch, and it will do at every iteration its job, and this is delaying, and it is also doing this. So we can put, for example, delay very at the top, because this gives us a chance that when we add further branches, that this will be also active there. Now the question is, what is the difference between having loop 1 and loop 2 changed? If I now put loop 2 above loop 1, then this makes a big difference. Because now we make for 5 iterations of loop 2, we make 10 iterations of loop 1. Let me plot here loop 1 over this, and we should see it here. This split is wrong. We can now see that we have here 10 iterations going up, 10 iterations going up, and so on. So this means for setting values like temperature, setting voltages, and so on, it is really important how the order of the modules is. But for measuring and for doing certain jobs of the modules, it is often not so important how the order is, because then they are still active in the branch and they can still do a certain task. And for each module, you need to read the wiki or the description to see how they work, when they are active, and so on. Okay. Let me check my okay, so these are the basics of how the sequencer works. It's basically a looping tool, a sweeping tool to go through different states of modules. The next important point is the phases of the SweepMe procedure. So I opened our SweepMe wiki that you find on our webpage. So if you go to our webpage and you go to Contact and Support, you find our wiki here. And if we go to the wiki, we can find in the programming guide the sequencer procedure function calls. This is a concept that some people often, maybe you don't even have to know this, but it helps definitely to understand a little bit how these modules work and what they actually do when they get active. Let's add an SMU module here. SMU module is a module to connect to a source measuring unit. I have here a source measuring unit from Aspect Systems. I click Find Ports, have the first channel activated. I create a voltage sweep from -2 to 2. And let's run this measurement. The delay can be switched off for now. And let's plot this data. And you can see an IV curve of an LED with a forward direction here at positive voltage, negative reverse direction at negative voltages. So let's go back to the web page. What is this SMU module now doing? It is running through all these phases and during the sequencer procedure. There are phases like connect, initialize, configure, power on, sign and transfer, and so on, and some other further functions. And these functions are called at different states of the sequencer. For example, connect and initialize, these functions are called once the entire measurement starts. So it is called for all the modules that are in the sequencer. We connect them, we initialize them. So we can make sure that even a module that is in a very lower branch, in a bottom, so in a branch that is maybe called after 30 minutes or started after 30 minutes, it is still in the beginning connected, initialized to make sure that these instruments that are used maybe later on already connected and they are there. So also the SMU module will connect to the instrument, check whether it's there, whether it's connected, whether the communication object is there. Then we have another phase or a part of the sequencer procedure where we go into a branch. Imagine we have multiple branches like this, another SMU maybe here. So SweepMe will now configure all the modules that are in this branch, in the first branch. And this means also that makefile is maybe configured and maybe delay is configured. All these modules could have basically the chance to do something. They don't need to do something at this point, but they can do it. And the SMU module will, for example, configure, and this means it will send the user configuration to the driver, and the driver can set all these properties and send it to the instrument. So this is typically done in the configuration phase of a module. Once every module of a branch is configured, the instruments are powered on, and there are some functions that go a little bit maybe too deep now, that are sign in and transfer, that are sometimes needed, but they are not needed to have a basic understanding. And then once we are configured, SweepMe starts looping through these iterations or through these set value combinations. And for every combination of set values, like different temperatures or different voltages, SweepMe is running through these functions. These are 1, 2, 3, 4, 5, 6, 7, 8, like so about 10, 12 functions that are just needed to make a single measurement point. For example, there's a start phase where an instrument can do something special at the beginning to prepare something. Then there's an apply phase. There it gets the new set value and sends it to the instrument. It can have a reach phase where it waits to reach this applied value. This helps often to send multiple set values to different instruments, and in the next phase they can take time to get to this set point. So you don't lose time by applying and directly reaching. We can split this. You can first apply, and then many instruments can reach their new set value at the same time and can make sure they are reached. Sometimes other instruments need to adapt to a new set state, new set value state. So one can use the adapt phase and so on in the drivers. Then there comes this measure phase or measure part where we measure and initialize or initiate the measurement or the acquisition of a data set. Then we can request the result, read the result, process the data, and bring it back to SweepMe. These functions are typically used in the driver, but they are also available in the modules. Typically, as a user, you don't have this access to these functions on the module level. This is what we do. But to give you a basic understanding, these modules are running now already through these functions and can do different tasks at a time. Once a sweep has finished in one branch, the instruments are powered off in the branch if they are not active in the next branch, and they are unconfigured. If they are part in the next branch like this here, then this delay module, if I would activate it, it would be part in the first branch, but also in the second branch. So it would not be unconfigured. It would stay in its state and directly continue here because it's still active. It doesn't need to be unconfigured. If the entire measurement was running through, SweepMe will at the end deinitialize all the instrument and disconnect them. So the sequencer procedure is also part of understanding how these modules work. And if you go through the wiki of each or through the wiki article of each module, and there's maybe sometimes written that a module is running a certain process in call or in measure, then it means that you know, okay, this is on the same steps like a certain driver is maybe starting a measurement, for example. Good. Let me check whether there are some questions in the chat. Not yet, I think. Okay, good. Then I will go to the next thing. We did now some first measurement, a simple measurement of an IV curve. And now we want to have a second channel. And this would be, for example, a transistor measurement. We have two SMU modules. One SMU module could be the one that is maybe controlling a gate electrode or gate contact. And the second channel could be an SMU channel that contact the drain, for example, and you get IV curves from your transistor, for example, output characteristics. I don't have now a transistor connected, but LEDs at these two channels. We can basically run this measurement also. The first is going from -2 to 2. The second SMU is going from, could be also from -2 to 2. And let's run this. And what we see is that at each point of SMU1, now the second SMU makes a complete sweep. Because this is not a transistor connected, but just two LEDs at each contact, this does not make much sense. But you can see also that we here have that we're going through this parameter space of the combination of around some 41 values for the first channel and 41 values for the second channel. Imagine you would like to synchronize both channels and would like to have that both channels run at the same voltage at the same time. Then there is the possibility, and this is one of the sequencer concepts we want to speak about today, there is the possibility to hand over values from one module to another. For example, I can select in the SMU module what I want to sweep. For example, I want to sweep voltage and where the value does come from. And here it comes from the sweep editor. This means this internal tool that every SMU module has where you can create a sweep. But you can also select a different source. And here I can, for example, select the sweep value of SMU1. This means the sweep value of SMU1 is here, are these voltages. And whenever a new voltage is set, it will also be handed over to SMU2. Let's run this and see what happens. We can see here the IV curve of SMU1 voltage. And if we plot the SMU2 current also over the SMU1 voltage, we can see there's a second IV curve and they have been measured at the same time while running here through the sequencer. So they have exactly the same voltage. This is also sometimes helpful when you want to have, for example, you want to measure a device and you want to have in the surrounding of your device, you have an electrode that you want to have at the same voltage like your device so that there is no leakage current in parallel or in lateral direction. So you can easily add another channel of an SMU and put it onto the same potential as the measured device to have every leakage around conducted to a certain channel, and so that you don't see this leakage current, for example, in one SMU. In this way, you can, for example, add many channels and let them run all at the same potential at the same time and go through many devices in parallel. It is also possible to use an external module or an additional module to create sweeps, like, for example, the sweep module. The sweep module is a module that is an arbitrary sweep generation module. It has different modes to create sweep values, like sweep box, or it can create a list of data from a file. Let's go to the sweep editor. Again, I make my sweep from -2 to 2. And now I hand over this sweep of the sweep module, so sweep value of sweep 1 to the first module, and I hand it over sweep value of sweep 1 also to the second channel. So I can have now one source that is independent from these two SMUs that is simply creating a sweep, and the sweep can be handed over to the sweep values can be handed over to different modules. So this is something that we try to separate in SweepMe. One is the connection to the instrument, but the sweep values can also be created in an independent way from each module. That we have often the sweep editor connected to the SMU is a convenience feature, so that you have an SMU module and you can directly create a sweep. But basically, you can also separate this. Let's run this measurement. And we see basically the same result. Now SMU module and SMU2 module, they get their result from a different source. But what is if we want to have running both modules in opposite direction? This means one is running from -2 to 2 and the other is running from 2 to -2. So we want to reverse the sweep value for one SMU. This could be, for example, the case that if you have a DC-DC converter and you need to apply a certain potential or voltage to these devices, and often you need a negative potential and the positive potential that are increasing in the same amount, in the same magnitude, but with reverse polarity. Let's do this. What we can do here is to add a calc module into SMU1, and SMU2 we put into calc. And the idea is that we still forward the sweep1 value to SMU1, but we also have a calc module that is doing at every repetition a calculation and creates a new value. And for this, we have here this execution in calc. And you can see before branch and configure, before each point, before start, before branch and each point in configure, and plus before start, and so on, or after each point and process. And these phases that you can read here are exactly these sequencer procedure phases that I showed you in the wiki that SweepMe is running through. So here it is really needed to understand which phases exist. We want to make a calculation before a point is started. So we use here before each point, so that we can calculate a new set value before the measurement or this measurement point is actually processed. For this reason, we take the sweep value of sweep1 as here, we define it as x1, and now we can type an equation in here and use minus x1. This means we have here the function y is a function of x1, x2, x3, and so on equals, and then you can directly put in the term that you want to use. Okay, so next step would be we go to our SMU module, to our second SMU module, SMU2, and now we select this calc1 parameter, and this should be now exactly have reverse direction. So let's test this. Yeah, I hope you can see it. The blue curve is SMU channel 1. Let's find. The blue curve is SMU1, and yellow or orange curve is SMU2, and now they have reverse direction. One is sweeping in this, and the other one is sweeping in this direction. With this trick, it is also possible to do something like x1 plus 0.3. Or let's say 0.2. Let's start this. And we can see we have shifted these curves. Now we have still plotted the SMU current over SMU1, so we would have to make a new plot. But this way it is also possible to make a sweep where, for example, the train follows the gate always by a certain distance and voltage. Yeah. Could be also an interesting measurement sometimes that is often or sometimes needed. Okay, so we have now seen that calc is a proper way to modify sweep values and hand them over to other modules, and so synchronize certain modules in their operation. Another way to create sweep values or to hand over sweep values is to load them from a text file, from a recipe file. This is what I will show now. I take here a read values module. Read values module is a module that can load text files or Excel files, and these files can be used to create recipes. I already prepared one. This is called recipe. It is in my custom files folder in the public SweepMe folder. It's really just a standard Excel file. And SweepMe passes this file. I can also show you how this file actually looks like. They open. This takes a short moment. And now you can see what I prepared. We have in the first line the names of the variables, in the second line the units, then there's a free line, and then I entered simply some values. Here you can use also Excel functionalities like to make calculations in between the lines to automatically let it increase or being dependent from each other. But what you see here, these sweeps are independent. This means voltage 1, voltage 2, voltage 3, voltage 4 can do independent sweeps here that you can program. Okay. And this file is now loaded, and you can exactly see the same data structure here. These are 51 lines of data for each variable. It's also possible to create different sheets. Here we use the sheet 1, and there are also some options to change the format of your file. But if this file is in like a standard SweepMe format, you can directly load it, and the data is passed into this tool. And what is it doing? It has a sweep mode, each line of file or each column as a list. This means each line of file means it runs through the first row, hands over these data, these variables or these values to the system, and you can hand them over to another module. Once the measurement point is finished, it goes to the next row, hands over these values to the system. We can hand them over to a module, it makes a measurement, and so on. It is also possible to parse or to load these data files as an entire list. So you can directly return a list and hand over a list to a certain evaluation function also. So this depends on your use case. Here we use each line of file. So we run through each row, and read values is doing an own variation now. Let's put this into makefile and take our SMU1 calc and SMU2 and put it into read values, and sweep1 is not needed anymore because sweep1 was one way to create sweep values. Now we use read values to create sweep values. And we go to our SMU1 module and tell the module to take read values voltage 1 as value. Then we go, the calc is not needed anymore. And we tell the second channel to use read values voltage 2 as the source for sweep values. So let's run this. And to show what this script is actually doing, we can show the voltage over time, because this is what actually is swept here. And you can see one SMU goes up, it stays there, then it goes down, it stays there, and the second channel is going is at the 0, then it goes up and goes down. Then it is not completely linear, also depends on the instrument. Sometimes it has to do some auto ranging. This will stop the further process from being linear. If you change, for example, the ranging mode and you have a constant range mode, then typically it gets also more linear. But then you also have to measure in one range. But the entire measurement was done in less than 1 second. So these are also smaller fluctuations. So using read values is also a core concept of SweepMe to create unconditional sweeps where each channel is doing a separate function. For example, this concept can also be used to control a robot. In read values, you can load, when I go back, for example, the positions of a motor to go, position 1 for X, Y, and Z. And then you can hand over these positions to a robot, and you can create a certain path the robot is moving. And if you combine it, for example, with other equipment, you can hand over some of the variables to a robot and some of the variables maybe to other equipment like a syringe pump. And you can build a dispenser robot with this module and the robot module and the other equipment. So basically, you can load and read values variables for different modules and can hand them over also to different modules, not just to this single instrument, but can be a combination of different instruments where you want to synchronize a certain process that is running through. This can lead to measurement procedures or to settings that are that become fixed. This means you have a setting that can run a recipe, and then you don't touch your setting anymore. You let's say you freeze your setting, you save it, you can load it, and the user can then just change the recipe file, select a different recipe file, and can run different recipes. So this is also a typical way how people use SweepMe, that they have larger and larger sequencer procedures, and then use recipe files to tell SweepMe what to do today and not change the sequencer every day, because the larger the sequencer it gets, the more work it is, of course, to always change it for every adaptation of a measurement. And this is also a concept that can be used to create probe plans for wafer level testing, where you have an Excel file or a recipe file where you define which measurement you want to do for which chip or die on your wafer. And then you can hand over these read values to modules or to conditions to do different measurements. Okay. Another way to create, to control your equipment is by using your scripts. And here I want to show you how to use CustomFunction for this. CustomFunction is one of the strongest modules in the SweepMe Pro, the Pro modules. It allows you to run your own script and hand over data from SweepMe to the script. It looks like this. It has a box for arguments that the script can define, and it has a box for variables that are returned. You can see here the description of the script if it has one. Let's open the example script just to show you and give you a very short introduction to CustomFunction. But basically, it is a Python file with a main class. In this main class, you can define your variables, units, and arguments, and SweepMe automatically passes these objects into the user interface. So you don't need to program a UI, you just define data types, and SweepMe knows, oh, this is an integer, I will make an integer box. Oh, this is a float, I will make a float box, and so on. And you can, for example, have a selection box, and it creates a selection. If you create, for example, such a tuple, an empty tuple, that is the hint for SweepMe to create an input box where you can select an external value. Okay, so now we want to control our SMUs and, for example, apply a sine wave. So let's do this. I go to my CustomFunction module, and first I copy the selected function. I take the example function and call it my control script. I open the script, and now I go quickly through and delete everything what we don't need. Right now, we want to have some return value. This return value has no unit right now. It's arbitrary. Probably it's a voltage at the end, but that's it. And we will kick out here all the arguments for now and make it really simple. Okay, so if I reload this function, you see the arguments have vanished, and the variables, there's just return value now. Now you can see that there are, again, these phases like disconnect, initialize, that you can use also in CustomFunction. For now, for today, we don't need them. So I will just remove them. This is a typical concept for drivers and scripts. You only need to use these functions that are relevant for you, and the rest can be deleted. This section of the example is just a section to check a script without SweepMe, just in a pure Python environment. I will also delete this. And now we come to the main function of a CustomFunction where you get the keyword arguments. This means the arguments that we define. There are none right now. And so we don't have to process anything. And we return our value. So, and the next step is we want to have the value defined. And the value should be NumPy is a package, and we want to use Sinus. NumPy is already imported. It was already part of the example, so we don't have to import it again. We can remove these things that we need today, that we don't need today, and that's it. And now the question is of what do we create design value? What is the argument? One thing could be that we use the initialize function again that I just removed a couple of seconds ago. And we create a timer. T start is time.time. And here I can create the duration is time.time minus T start. So we have now the time distance. Since we measured the program flow, this duration can be handed over to the sinus function. We can multiply it times 2, so our voltage will be between -2 and 2 that we return here. Okay, that's it. So now we want to go to SMU and hand it over here, and we can select CustomFunction 1 return value. The SMU2 I will remove for now to keep the example as easy to understand as possible. And if I run this once, we say no time defined on the script. Okay, let's fix this. For some time. And let's run this script. And what it basically does, it makes one measurement at the start value of the SMU, but it is not running forever. So now we need to add a loop module to keep this process running, because we need to create somehow an iteration. What we cannot do is to tell the SMU to make a sweep, because then the SMU has already a sweep defined. We need an external creation of values that is running in a loop. And here one concept is to use simply a loop module that is creating some kind of an event loop. I put this to endless mode. So what this thing is doing now, it runs forever, and CustomFunction is constantly doing its job. Loop is doing its job. It's constantly creating values. And in the next turn, SMU can get this new value and apply it to the SMU. Let's see what happens. And this is now the real measured voltage, or the voltage at the SMU. And this is the, let's say, the voltage over time. And we have created a script that is now controlling our SMU1 in a more individual way. Let's also add here the current on the other axis. And you can see this nice nonlinearity, or this rectification of the diode, that it gets a high current in forward direction, but it's always 0 at -2. Okay. And I think this gives you some kind of idea how to create more complex handling of the equipment. It means you can add multiple equipment pieces or modules into the sequencer, and then you can write a script that is doing a very special procedure with it. This means we could also have a second value returned that is controlling a second channel, and we can, for example, return value 2. Then, of course, I would also have to add variables and units. Okay. Another concept is that we want to sometimes do a certain task in SweepMe, for example, an optimization routine. And once the optimization has been finished, we want to skip it and go to the next branch. This can also be done here by, for example, adding a condition module. I add this condition module at the bottom. I could also add it higher at the end. It will also be activated at every repetition. And whenever it is activated, it can do a certain task. Here I also have this execution field where I say, when do we want to use this condition? Here I want to use it after each point. This means always when a measurement point is finished, I want to make a check and check a condition. Here I could, for example, say if the voltage of SMU1 is larger than 1.9, then we can skip the current branch. This means this script will run, and once the voltage is very close to 1.9 or above, it will, also when it is above 1.9, it will skip this branch and goes to the next one. Because there is no next branch, nothing will happen. It will simply finish the measurement. Let's check this. So we have seen here voltage was increasing, or here the blue curve, voltage is increasing. And when it passes 1.9, we can skip this branch. Now we could add also here a loop module with 100 times. So what we are doing is we are now in the first branch, we are looping until the voltage is at 1.9 volt. Then this branch is finished. We skip it with the condition. We go into the second branch. In the second branch, we have 100 repetitions, and the SMU1 is still active. It is part of both branches. It is part of the first branch, going from make file to condition, but it is also part of the second branch, going from make file SMU to loop 2. This means SweepMe is keeping this SMU1 active and is keeping it as its voltage that has been the last time set by this first branch. And now you can do a repetition at this value, for example, a check over time, or you can do other sweepings. Yeah, but this is also a basic concept that you have a combination of loop and condition. You loop until you have reached a certain state, and then you can trigger a condition. The condition could also be created in the custom function. For example, we could have another variable that is, for example, also called a flag. This means this is just a Boolean value that tells us whether we can also call it success. This means whether this operation has been finished and is correct. And we can say success equals duration larger than 10 seconds. This success value is a Boolean and will be returned as well. Reload the script. And we now see that custom function is also returning the success parameter. I can go to my condition and tell that it should probably have to go once there to the sequencer to refresh. Yeah, here's the success value. And if success is true, we can skip this. Let's run this. This measurement should now run for 10 seconds. And after 10 seconds, it has started. It starts with these 100 repetitions in the second branch. You can see here a certain gap between 10 seconds, but you can also see that the measurement started a bit later, and the script is taking the time exactly when the measurement starts. So it's exactly 10 seconds when it goes ahead or goes further with the next branch. This is, for example, a typical scenario that we also use in automation of process chambers. Imagine you have a vacuum chamber, and before you want to start a certain process, you want to wait until the pressure is okay. So you can create a loop that is constantly measuring the pressure of a pressure controller. And when the pressure is, let's say, below 10 to the power minus 6 millibar, the condition can skip the first branch. We don't need to wait longer, and we can start with the deposition process, for example, in the process chamber. This can also be a way that you can control constantly whether a pressure is okay in a process chamber, and then you can skip the entire measurement when the pressure is not good anymore. Okay. Yeah. Now I hope this gave you some more ideas how to do some more complex looping, especially in combination with condition and custom function. A question that often arises is, how do we actually use if-else in SweepMe? So what we don't have in SweepMe here is an if-else module in terms of, if this is done, then please do this, and otherwise do this. You can have conditions that can trigger certain branches. I will show this in the next step. But basically, you don't see directly if-else. And why is this the case? The reason is we want to have reusable modular content in SweepMe. If you start with if-else already on the module level, then you come very quickly into individual code, as you know it from Python, LabVIEW, or MATLAB. And this means you write already a very individual program where the components are often very difficult to reuse, and you end up in a program where you cannot share easily contents. The idea in SweepMe is to move these if-else decisions into the drivers or into the scripts. This means into the custom function scripts. And by this, you can hand over information to your custom function, for example, some input value. Let's define it here. Input. And this could be, I think it's, was it a double point? So now, yeah, was also shortly confused. I have now created input value. I can hand over some value from the system, like for example, a current. And here in this script, you can now just as usual use your if-else. But the advantage is that it is encapsulated in a script. And in the best case, you have a very clear interface of information that go into the script and to information that get out of the script. So then it becomes a robust function that you can share, that you can give somebody else. If this function is well written and very generic, many people can use it. For example, to have a generic database access, or to have a generic code or data handling for a certain process. And then you can still combine it with different equipment. You can combine it with a parameter analyzer from company A or company B, for example. And this is why we try to shift these individual code into scripts that then become modular pieces that you can reuse. So often it's also the case that in the drivers, you have also often if-else. You hand over, for example, certain decisions and information like your speed and integration time or your compliance value, and the script can handle all these things then in direct code. The last or the next thing I want to show you, I see we just have 5 minutes to go, but I think it's still enough time to do this, is that you can also use conditions to run certain measurements. For example, you can use a condition module with makefile, and here we add an SMU module, and this makes a certain IV curve characterization, and then we take another condition module. We have maybe another makefile module with a different name later on, and we have another SMU module that is also doing a different measurement. Let's configure this quickly to really show you the measurement. Again, from -2 to 2. And here we use the first channel. And for the second SMU, we do the same. We use here the second channel and run from -2 to 2. So we have now 2 measurements. One is doing the measurement at the first channel. One is doing the measurement at the second channel. We can now also tell condition to skip the entire branch when there is a certain state not reached, or when there's certain information is given or not given. And to show you this, I can use a form module. We have to put it here on the top. The formula module is a module that creates an empty widget, and we can now fill it with a checkbox and call it do measurement 1. And another checkbox, do measurement 2. Let's go to our condition modules. The first condition, we say do measurement 1 is true, is not true, also, or if false. And then we say skip current branch. The same we do now for condition 2 with the second measurement. Again, we say is not true. And if this is not true, we skip also this branch. Okay, I start the measurement. You can see nothing happens. Identifier channels has a problem. Let me check this. It's okay. And that looks also okay. Let's switch on one measurement. Let's see what it is. Okay. Do not immediately know what is the problem, but could be a relation between the 2 modules when they are in different branches. This is what I have to check afterwards. Maybe I will do this first now with one branch. And you can see this measurement went through for the first SMU. And we see this measurement. Let's do this again. And if I uncheck the first box, oh, here's this Microsoft Teams bar in the way. So if I uncheck this, we can see it still doesn't run if I have not checked the measurement. Anyway, what I wanted to show you here is, this is sometimes also related to the drivers and to the instruments that I have to check afterwards. But what I basically want to show is you can use conditions to say, I want to make this measurement or I want to do another measurement. And this way you can do a little bit something like an if-else. But this is sometimes really important to do it, because if you have a big probe plan and you have, for example, at a wafer prober, different measurements planned, like IV measurements, CV measurements, or different types of IV measurements, you can add to each branch, to each measurement, a condition, and then use either a formula module or a read values module to hand over which measurement you want to do for a certain die. And by this, you can also skip or switch measurements that you don't want to do and create larger measurement plans.